All right, well, hello there. My name is Chris Orban. I'm a professor at Ohio State. But I did my undergrad at the University of Illinois, so I spent lots of quality time with the corn over there in Illinois. So I appreciate you all letting me talk about what we're doing. So yeah, let me just go ahead and jump into it. So a little bit about me is that I got my bachelor's in physics from University of Illinois, and then I went to grad school at Ohio State, so I've been in Ohio ever since. But I am a computational physicist, and that means that I use computers to solve physics problems. And so I do fundamental research in plasma physics, but I also do a lot of education research. So I have a unique perspective in sort of the whole computer science world. So a lot of computer science education is done by people with computer science degrees, and they have their approach. Mine is different, and I'm going to illustrate that difference to you, and hopefully you may be able to find it useful in your math classes, your science classes, etc. So the STEMcoding project started in 2017. That's when we launched our YouTube channel. So if you go to YouTube and search on STEMcoding, you can find us. And we also started creating Hour of Code activities. So the world's most popular computer science education website is hourofcode.com. And so we put, not the first, but some of the first science activities on that site. And so we started with physics and video games activities, which I'll talk about in a second. But then we expanded into all kinds of different subjects, which I'm going to hop around today. Something I'm not going to talk about, but in Ohio, I am part of an effort to create a high school math class called Discrete Math that is a mix of kind of Algebra 2 level math and computer science. And so I'm really happy to be part of that. I'm not going to be able to talk about it here, and I don't speak on behalf of Ohio Department of Education, but please email me and ask me more about this project. I'll be happy to share. All right, so here's kind of a timeline of what we've been up to. Is that we started with an hour code activity in 2017, which I'll talk about, and we kind of kept on going here. So a fun activity that we developed is the asteroids game. The asteroids game actually has really good trigonometry in it. So it's a good way to talk about trig. It's a good way to talk about Newton's laws. F equals ma, all that sort of thing. So asteroids is perfect for that. I mean, the laws of physics are simplest for a rocket moving in free space, and that's what the game of asteroids is. We also have a game called Lunar Lander, where you're trying to land on the moon. And then again, there's some good physics there as well. And then Pong, this is actually one of the simpler activities. So Pong is actually, when the ball bounces off of things, that is an energy conserving collision. So we call that an elastic collision. And so if you're teaching concepts of energy, say for a physical science class, this is a great thing to do. So these activities are maybe more like 10th, 11th, 12th grade. This one you could probably do with 8th graders if you had to. And then we continued. So we put the first activity on hourofcode.com where you're calculating the digits of pi. And so I'm going to talk about that in just a minute. And then in 2019, we got really excited about the black hole image. You guys remember the black hole image from the Event Horizon collaboration? So this is a nice photo from this is Katie Bauman, and I believe she's a computer scientist at Caltech. And I love this photo for so many reasons, but to me this photo shows that the way that modern science works, and this is key to sort of our whole philosophy about all the stuff we're designing for high school and middle school stuff, the way that science currently works now is very interdisciplinary, where you have physicists and mathematicians and statisticians on this project in particular, radio engineers, computer scientists, all working together to solve a problem. And with the Event Horizon telescope, which is not really a single telescope, it's a network of radio telescopes across the globe, we have been able to point those radio telescopes at approximately the same location. We've been able to do that for probably a couple decades. What we could not do, and what we didn't what took many years to figure out is how do you stitch together all the different data from those telescopes to make them into one super radio telescope. And so the biggest challenge was as much a computer science challenge as it was a science challenge or a physics challenge, something like that. So that's what this shows to me. And so I think that if you're going to teach science, if you're going to even teaching math, it's important to integrate computer science into that, because that is how those disciplines work. So I give an example from physics. Same thing with mathematics. So there was an article last year. There was a mathematical research paper in which they provided a terabyte of data showing that every possible combination, satisfied this conjecture, and that's how they proved the conjecture. So computer science and math and physics are so linked that it's kind of ridiculous that we would ever think of teaching these subjects without connections to computer science. Here's another picture of Katie. So these are all the hard drives that have all the data that the telescopes recorded. So we got excited by this, as you can tell. I'm already excited about it. And so we created 2 activities for our code, talking about, I guess it's one activity that has two parts of it, but talking about the escape velocity near objects in general, so like launching a rocket from Earth, but also if you're close to a black hole, how does that escape velocity depend on your distance to the black hole? And at some point, the escape velocity becomes so large that you can never escape from the black hole. And so we talk about that. And the math here is kind of algebra 1-ish, algebra 2-ish math. So it's not like we're getting into tensor calculus and all that stuff. It's actually at a level that people could potentially digest. All right. And then in 2021, as I said, we started to get into environmental science. And so we started getting really interested in data science, which is sort of this hot new field. For us, data science means making sure students have good spreadsheet skills. I think, obviously you can go into data science all the way into neural networks and all these things, but for us, it's important for students to have a solid foundation in spreadsheets, to not be overwhelmed or anxious by using Google Sheets or Excel, that sort of thing. And so we created this activity that has to do with like the seasons and stuff. I'll talk about it in a minute. We created this activity to kind of be an adventure into that. So I'm going to go ahead and jump into this now, because I promised this would be a hands-on thing. And so what I'm going to do is I'm going to click this link, go.osu.edu/birthdaycoding. It's going to come up. You're going to need to bear with me as I move my screen here. There we go. Thank you very much. All right. So here's our code activity. And the premise of this activity is that in other states, so Ohio, Illinois, the Midwest, right? Climate change is not quite as obvious as it is in other parts of the country. California has wildfires. The West has droughts. Florida, so I have family that lives in Florida. There is a slight increase in the number of hurricanes, and the hurricane strength is a little bit higher than it is due to climate change. But in the Midwest, it's not as obvious the effect of climate change. So this activity kind of explores that. And the main question we're trying to answer is that because of the average temperature getting warmer across the globe, how many fewer days of sub 32 Fahrenheit weather do we get per year? I don't want to say shortening the winter, because the winter is controlled by the sun and the moon and all that, right? But how many fewer days of frosty weather do we get each year? You could also think of that as how much longer is the growing season, that sort of thing. And so what is that number? how many days of sub 32 Fahrenheit weather have we lost in a year due to climate change so far? Is it a couple of days? Is it a month? What is it? Is it a week? So that's what we're going to try to assess. So so I'm going to go ahead and click through here. So it's designed so that you can't just skip ahead, and that's intentionally designed that way. So I'm going to click next here. And the first thing you do is you go to Google and you collect climate data. So the example here is Columbus, Ohio. And by the way, there's a video here you can watch. You don't have to watch me. So if you go to our YouTube channel, you get a nice video on how to do this. So you all are in Illinois. So I'm gonna look up my old college town, Champaign, Illinois, climate data. All right, so there we go. I know Champaign-Urbana is more than a college town, but there's a lot going on there. But all right, so this is what you want to try to find. So you want to try to find, all right, well, on the coldest month of the year, so it's January, it's kind of between, the high is kind of 33, the low is 17. Pretty chilly, a little bit chillier than Columbus, where I live now. And then the winter, the high, the warmest month, the high is 85 and the low is about 65. So that's the information that you need to do this next part. And so what you're going to do is you are going to sort of take that, all right, so maybe write those numbers down. And what you want to do is you want to calculate sort of, we have a high and a low, right? But what's the typical temperature in January and what's the typical temperature in July if you sort of average these two numbers together, right? So maybe I can break out Desmos here. Desmos, just do a simple average. So let's see. So the average of 33 and 17. Okay, that's 25. So the average temperature in January is approximately 25. 85 and 65 for July. I'm going to do that one in my head. It's going to be 75 is the average temperature in July. All right. All right, so I've got that. What do I do next? All right, so now we're going to open up this code in a code editor. And I can go ahead and press play here. And this is what I get. So this is the average temperature through the year. I mean, there's no randomness added to it. We're going to put randomness to it in a second. And the green is sort of what it is, historically. And then the red is if you add a shift to that and you just sort of count the number of days of frosty weather, right? And so we're going to steadily add, increase the average temperature, and we're watching the number of cold days lost, right? Now this is for, these numbers are for Columbus. Columbus is probably going to be pretty similar to Champaign, but Champaign is, coldest day is 25, the highest day is 75, so it's pretty similar. And so it starts out that according to this, in other words, according to this, we would expect on average about 90 days a year of sub 32 weather. But if you include a shift, at some point it's 76, at some point it's it's 74, and eventually it's going to be 0, right? So eventually, as global warming continues to grow, it's going to, there wouldn't be any frosty. I mean, there just wouldn't, right? So that's the next step here. Now you can make this a little bit more realistic if you want to. By the way, this programming environment is P5JS, so this is run by a nonprofit in New York. So great group of folks. Please don't hesitate to allow your students to. I don't run this nonprofit, but I've never gotten an email from these people. It's a great group of folks that run this website. So we just modified this, okay? Again, you don't really have to understand that this is a cosine wave to sort of be able to do this activity. If you want to talk about that it's a cosine, that's great. You can look at that function there, but you don't have to. And so then you can run the code, and then a fun thing you can do is to add some randomness to it. So you can have this little copy code thing, add a little bit of randomness to it. So that would be, I think it's here. Just Control V to paste that in. And I live in Columbus, Ohio, not very close to a body of water. I used to live in Champaign, Illinois. So I know very well that the temperature in those places is pretty good approximation to random function, plus or minus 10 degrees. I think last month in Columbus we had a 40-degree jump from one day to another. So what you could do is you could have your students, sort of change this range to try to get it to be more realistic. But the point is that when you include randomness, and then you have some overall shift there, you're still getting fewer sub-32 days. And so the reason that we add this is not just because it looks cool, it's because it's important to talk about the difference between climate and weather. So there can still be an extra warm or extra cold day, but there can still be these shifts. And you kind of see this graph on the bottom. There's those trends. So we're designing it to help provoke that discussion. So I'm going to go on to the next one, but another part of this activity is downloading this data to a CSV file, analyzing it in a spreadsheet. You can find the hottest day of the year, the coldest day of the year. You can do sorts and that sort of thing. So there's a lot to dive into, and you can also, if you're curious, you can change the threshold of let's see. You can change the threshold, if you follow the directions, you can change the threshold from 32 Fahrenheit to something else. So if you're interested in the growth of sea ice. So sea ice is salt water, and so you have to be colder than 32 Fahrenheit to freeze seawater. And so you can put in that temperature and try to think about Greenland, melting away, that sort of thing. So there's a lot you can do here. You can also think about mosquitoes. Mosquitoes tend to breed when the temperature is above 50 degrees Fahrenheit. So as the Midwest gets warmer, we're going to have more mosquitoes because that's what they see in the southern states. So you could use that so there's a lot of different things that you could use this activity for. Okay, so how do we connect with physical science? So in Ohio, physical science is like a 9th grade, 8th grade sort of thing. Some other states has different names, but so this is one of the first activities that we created. It's called Move the Blob, and this is not the activity. This is the game that the activity is inspired by. So this game was popular. This is a game called Agario. This was popular maybe 5 or 6 years ago. Some kids still do play this game that I've talked to, but let me show you what our coding activity that's inspired by this looks like. So if you go to, hopefully you saw the link, so go.osu.edu/movetheblob2, you can follow along. Come on. All right. So here it is. So this is the coding activity. We have videos for how to do all this, by the way, on the YouTube channel. And so you're going to click this link here to open up the code editor. And so this is the code. This is all the code. It's 37 lines, not too bad. If you want, you can sort of click this little button and see the rest of it. I'm going to go ahead and press play here. And there's a little circle over here. And if I press the right arrow key, the circle will move to the right. But if I press the left arrow key, up or down arrow keys, then it doesn't do anything, and I get these sort of X's of get the blob to move to the left. Well, it can't move to the left. So we have to look at this code, and we have to modify it to get it to go in all the different directions. So for example, when you look at, so this code has something to do with the left arrow, right? And it says if key is down, left arrow, do nothing. That's probably why it does nothing when I press the left arrow. Okay, so I'm going to have to replace that with something. If you look at what it does for right arrow, it says Vx equals 10. So if you think about it, Vx equals minus 10 would make a lot of sense for left arrow because positive x is this way and negative x is that way. Right, so if I do that, now I can move this thing to the right. If I press left arrow, yep, I can move it to the left, I get a nice little green check, that sort of thing. But if I press up and down, it doesn't move that way. And so there's a couple of steps you can do. You can say, all right, okay, well, when I press up arrow, if key is down, up arrow, do nothing. That's probably why it does nothing. So it's important to remember that up is in the y direction, so you need a Vy there. So I can try this. Right, left. If I press up, now I get an up arrow, but I don't actually get to move upwards. Okay, so we're missing some things. So for example, we're missing, if you look very closely here, you notice that we're updating the x location, but we're not updating the y location. Okay, so I can add that in, times dt, and there you go. So now we can move upwards. We still have this issue now that we're drifting. We're not supposed to drift, and we got to figure out how to fix that. But that's sort of the gist of the activity. There's also a follow-up to it called Accelerate the Blob, where the arrow keys control the acceleration, and you can have a conversation about what's more realistic. Is, just having something that starts from rest and just sort of jumps to some speed and then stops immediately, or is it more realistic for things to accelerate? And so I really like Move the Blob and Accelerate the Blob because it kind of shows how you can make these video games, more realistic as you go, and maybe they're a little bit more fun as you make them more realistic as well. Another important component of this activity is that positive y is up. So remember I said earlier that I am not a computer scientist? Well, that's a good thing because computer scientists would have put the axes for this thing up in this corner of the screen. So they would have put positive y as down and plus x as to the right. So for example, 0, 0 would be up here, and larger values of y would be down, and it would drive everyone crazy. But the computer scientists would say, well, this is what we do, and so I've flipped it. So I'm using the traditional math coordinate axes because I'm designing this thing for like 8th graders. Code.org thinks that, our code thinks that 6th graders can do this. I've seen 6th graders do it. I think it's important to just not completely, there's so many new things here. Let's just try to keep the coordinate axes the same thing that 6th, 7th, 8th, 9th graders have seen, right? So that's Move the Blob. That's how I connect with physical science. Come on, gotta click through here. Yeah, so here's Accelerate the Blob. So you can see that your the arrow keys are controlling the acceleration now. So it's kind of a little bit more interesting of the dynamics there. All right. So for a full list, and there's a very long list of physics and astronomy. I even go into electromagnetism, that sort of thing. So please check that out. How do we connect with math? So I mentioned earlier we were the first group to put an activity on ourcode.com in which you calculate the digits of pi. My whole attitude about computer science is that I am not here to teach computer science for the sake of computer science, right? You should not put computer science into a math class for the sake of computer science. You should put computer science in a math class so that you can use a computer as a tool to solve math problems, right? And that's what we're doing here. We're using a computer to calculate the digits of pi. Okay, so we're going to go to go.osu.edu/pi-day-hour-of-code. So we put that in the browser. That will take me to, let's see, if I put that in the browser, that will take me here. So this is our hour code thing. You can also find this video on our YouTube channel. And I'm going to click this link to open up the code editor. All right, so there is the code. Not a whole lot going on here, only 16 lines of code. And when I press play, there's not going to be a whole lot that happens. So we're going to start pretty small. So I hit play, and you'll notice that the origin of the coordinate system is in the middle here, not down here, not up here, but it's in the middle. And if you look closely, you'll see a little dot right here. So x is 0.5 times this radius, y is 0.5. So a little dot here. The idea of this activity is that what we're gonna do ultimately is that we are going to calculate the digits of pi using a random number generator. We're going to put down random points, and we're going to check if those points are within this circle, right? This gray circle, or if they're within the square. I mean, presumably they're all within the square, right? But some of them are within the circle, and the ratio of the points within the circle to the square turns out to be pi over 4, right? Because the circle is inscribed in the square. And so if you can calculate that ratio, then you can, which is supposed to be pi over 4, well, you can just multiply it by 4 to get pi. That's ultimately what we're going to do. So some good geometry concepts. This is be good for a geometry class. So that's what we're going to do. There's some directions here that I can follow that tell me what to do next. And the first thing is to, instead of just putting down one dot, I'm going to replace this with a random number generator, and now I get a whole bunch of dots. But I'm not clearly identifying whether these dots are within the circle, within the square. Like, they're all the same color. They're all just black. If you want to change the color, you can. That's a fun part of this activity, is to change the color. All right, so that's fine. And so then the next part is that, all right, well, I need to put in an if statement here that gives the dot a different color. So I'm going to erase this draw point command, and I'm going to replace it with this thing. And so we give the students this part, but we don't tell them what should be in the if statement. We just say that, well, if something is less than something else, then draw the point with this color. But if not, then draw it with this other color. So in here, it's black or gray, right? So what you got to do is you got to figure, all right, well, what is the distance between any particular dot to the origin? And if you think, yeah, isn't it nice how it kind of fills out over time? That distance, well, that's just the hypotenuse, right? So there's some x here, there's some y, and then there's some distance to the origin, right? And so here I can just say, all right, well, this has got to be if the square root of x times x plus y times y, right, x squared, is less than something. Well, what is that something? Well, there's a radius here. So there's a certain radius of this circle, which has this variable is here. I think it's 200. I can't remember the number. Radius. Now, if I do that, then it should give me different colored dots, depending on how close we are to the origin. Okay. So that seems to be working. Now, this doesn't get us the digits of pi yet. We have to keep track of how many points are in here and how many points are in there. So that's the next thing we have to do. But isn't it fun to watch it as it fills in there? So now we gotta let's see. So we can add some code. All right. Every time I draw a point, I'm gonna increase it by 1. Right. So I've already declared these variables for you. So endpoints is 0, endpoints in circle. So I got to figure out where to put this one. So the question is, do I put is this the part that's inside the circle, or is that the part that's inside the circle? So I have to choose between these two, and then I can get that ratio. I believe it's this one is the one that's inside the circle. And so some of these are inside the circle. They're all inside the square, so I don't need to put this in the if statement. And then I can take the ratio of endpoints in circle to endpoints total. And if I multiply that by 4, it should tell me, let's see if it's going to work. It should give me an estimate for the digits of pi. So if you look down here, you see that as time goes on, it takes a while, but it's sort of hovering between 3.2 and 3.1. Yeah, it takes a while. It takes a while before it to converge. So this is not a great way to estimate the digits of pi. But there's ways to speed it up, like there's a way to add a for loop. We tell you how to do that. Anyway, but this does work, and then as you're waiting for that, you can like change the colors and that sort of thing. So this is how we would connect with. So again, this is using a computer to solve a math problem, which is what is the digits of pi. So in the math lingo, this would be called a Monte Carlo method for determining the digits of pi. There's other methods as well. All right, so that's that. So a full list of our math activities is here. So there's a very long number, more than I have time to go over in this presentation here. I already talked about environmental science, so I'm not going to go over that again. But I should say that this is part of something we're working on. We're trying to create a year-long data science course. So if you look out there in the education space, UCLA has a year-long data science course. Stanford has a year-long data science course. Again, this is for high school level. And we are trying to create a year-long high school data science course. And the thing that is different about ours from the others is that we're emphasizing spreadsheet skills. And we're trying to design it in such a way that students could take the Excel industry credential test at the end, which is not a particularly difficult test. It's not like crushingly difficult like many industry certifications are. But the idea is that we're going to try to do data science in a way that connects with science and connects with environmental stuff, but also gives them some workforce skills as well. And so if you're interested in that, I'd love to talk to you. And we're designing it now, so if there's something you want us to design and an idea you have, or we'd love to get that feedback. So this is one of a couple of data science activities that we have now. So that about covers it. I didn't have time to talk about the object tracker, but this is a fun thing you can do to track objects, and then it creates this data you can load into a spreadsheet and analyze. So that's a fun hands-on thing that students can do. We've got our YouTube channel here. STEMcoding is also a nonprofit, and so we have this nice learning management system that you can use. So if you want to send me an email about that. So this site has all of our activities in one place, and it has tools for teachers to be able to implement them into the classroom, and sort of basically to help grade it, to kind of help keep track of student submissions and that sort of thing. So let me know if you're interested in that. Please follow us on social media. We're also on Mastodon. And there's also an email list that I send out. Send an email about once a month. So I could talk all day. I could talk about some of the education research we're trying to do. But STEMcoding is being used in many different schools across the United States. And currently on this site we have over 2,000 high school students registered on that site. Yeah, we're always growing and always open to chatting with people about what they'd like to see. But thanks for your attention.